To the CAM Manager webinar, Platformization of Molecular Design, Innovation via Digital Transformation and Advanced Simulation. My name is Ralf Kempf. I am Editor-in-Chief of CAM Manager International, and I am moderating today's webinar. Our speaker today is Dr. Jörg Weiser, Managing Director of Schrödinger, Germany. He will explain how Schrödinger's molecular design platform integrates physics-based predictive modeling, machine and deep learning, and enterprise informatics. Some case studies will show how this platform supports research and development in the industry. Welcome, Jörg. Before we start, I would like to give you a few details about the course of the webinar. You should now see the title slide of the presentation on your screen. This is an interactive webinar, which means that you can submit questions at any time during the presentation. To do so, please use the small window below the actual presentation window. The presentation itself will take about 36 minutes. Afterwards, Jörg will answer your questions. If your specific question cannot be answered in the discussion, our Schrödinger expert will get in touch with you by email after the webinar. And finally, a note on our own behalf. This webinar will be recorded and then made available on our website, cammanager-online.com/en, as an on-demand webinar. All registered participants will be informed by email as soon as the recording is available. And with that, I now hand over to Jörg and look forward to his presentation.
Thank you very much for the kind introduction, and hello everyone. In this webinar, I'm going to talk about platformization of molecular design, where I will start with molecular design, then platformization, and then how these two concepts are coming together. So, molecular design, it turns out that the field has been trying to come up with algorithms to solve that problem for decades. The approaches can be broken down into two categories. Number one, knowledge-based machine learning, what for better or worse is now often referred to as artificial intelligence, AI. This has received a lot of attention recently because of its ability to beat humans at chess and Go, recognize faces and photos almost as well as humans, and drive cars almost as well as human. So the obvious question is, how good is it to design molecules? The other approach is to develop rigorous first principles physics-based models that accurately describe the true physics underlying the molecular properties. This requires major advances in the underlying science of molecular interactions and also major advances in compute power. A group of young people playing a game of frisbee. Everyone on this call will have come to the same conclusion much faster than me reading that sentence. So what is so spectacular about this photo? This photo was published in the New York Times on 17th of November 2014, which was 5.5 years ago. However, the text wasn't provided by a New York Times journalist. It came from Google's deep learning program. That program maps a string of words to colored pixels. In other words, it gets trained by a huge variety of photos with associated linguistic descriptions. By then, and I would still think today, that's an amazing performance of a computer program. But that's what it is. Great performance, but there is zero competence included. The software does not know what a frisbee is. It does not know what people are. It does not understand that it is probably more fun to play frisbee when the sun shines opposed to snowfall. In other words, the program has no contextual understanding of what is going on here on this photo, unlike all of us on this call. I leave it up to you whether you would call a computer program intelligent that has great performance but lacks any contextual competence. We're coming back to this thread later. Now let's have a look at a comparison between a knowledge-based machine learning deep learning approach versus a physics-based modeling approach. We're looking here at a molecular property, in this case a binding affinity to a given protein target. This is just one example. It could be any physical property we're looking at, for example, an excitation energy of an organic LED or a glass transition temperature of a polymer. The question is always the same. How well can we train a computer program with machine learning or deep learning methods? So let's have a look at the two arbitrary molecules in this training set here. The affinity of the hydrogenated one is 6.9. The ethylated one is 7.1 here on the left-hand side. So one would guess that the methylated molecule has an affinity of around 7, which is a straightforward interpolation both for human intuition as well as machine learning and deep learning methods. Now let's replace the methyl with a hydroxyl underneath, on the right-hand side, underneath the methyl, and ask for the affinity. That's both very challenging for human intuition as well as machine learning and deep learning because of the orientation of the hydroxyl towards the binding site, its protonation state, the balance of protein-ligand interactions versus desolvation effects. In this case, a physics-based computer simulation, as in our free energy perturbation method, is highly predictive and outperforms machine learning as well as human intuition. Now let's turn to the other part of my presentation's title, platformization. The isation describes a process over time, so let's have a look how platforms have developed over the past decade. The majority of the 10 most valuable companies on the planet are now digital platform companies. What do these platform companies have in common? Do platform companies sell data? Is data the new oil of the 21st century, as often used metaphorically? Or are data like sunshine, in other words, free to have, and the contextual output is the only value? There's no clear answer to this. Most data never change hands, so they are not traded like oil. But in some cases, they are traded like oil, for example, in the advertisement industry. Also, the governance of ownership of data is handled differently across the globe. In the US, they are handled like oil. In other words, who attracts the data owns them. In China, they are public goods. In other words, they're all owned by the government. And in Europe, data are more seen as privately owned. All of the above makes it very hard to have a global business model just based on data. So if the business model of these platform companies is not the common denominator, then let's ask the question, what makes these platforms so successful? So what do they have in common? So one thing is real-time analysis of digital streams to increase efficiency and usage of a platform. So that could be real-time analysis that is self-driving cars or traffic control. The platforms are digital ecosystems where value-generating interactions between groups of people take place. So value interactions, for example, take place on business networks like Xing or LinkedIn, or one purchases goods on Amazon or Alibaba and gets feedback from other buyers. Platform becomes the center of attention It is now a must-have, not any longer a nice-to-have. And if that's the case, if it's a must-have, it acts as a gravity center. So, in other words, data attract even more data. The center of attention also means one doesn't want to stay in a silo any longer. One wants to go where everyone else is. So digital transformation of the world over the past 10 years was achieved via platformization. I think it's fair to say that this process is irrevocable on economic life as, for example, railroadization was in the 19th century, which started in 1830 when the first intercity railway in the world opened, the Liverpool-Manchester Railway. That process of railroadization was hugely successful and is still ongoing until today, bringing people and economies together. Now let's have a look how these platform principles of real-time analysis, value-generating interactions between groups of people, as well as data gravity may work in the context of molecular design. This is a view on our molecular data with our enterprise software Live Design. You see here molecules with associated experimental and calculated properties. You can view the molecules both in 2 dimensions or 3 dimensions. You can see contextual information like, for example, the alkyl chain needs to be optimized, as well as action items for follow-up on colleagues or collaborators. More importantly, all data is live, which brings everyone on the same page. There is no data silo. There is no withholding information. There is no secret wisdom available to a few people. In other words, this is pretty democratic and allows everyone to draw conclusions and sharing those with everyone. A platform is not only about data, it is about contextual understanding by creating knowledge around data. In this case, 3D visualization of a molecule in its environment. Here's a great example for real-time analysis. Suppose you're sketching a compound and you wonder whether exact matches or substructures already exist while you're sketching your compound. Today's speed allows you to search across 1.5 billion compounds in a quarter second. That's not only highly interactive, it's actually faster than Facebook. Even something complicated like accurate docking of a molecule with the right orientation in a target protein can be done in real time. On the left-hand side, you can change the structure of a molecule in 2D, while it simultaneously docks in 3D on the right-hand side. Suppose you have different users with different scientific background, then the same data source may require different contextual representation of data. But if the users are not siloed from each other, they could actually collaborate. Being live allows for global collaboration, and today's computer performance allows for a large number of users working on the same live report with the ability to express and contextualize the project data in zillions of ways. Annotated insights by user 1 in this example would then be immediately visible by user number 2, which would then lead to an efficient scientific discourse, and that, the discourse, is the core principle for scientific progress. That brings me to the hypothesis that any molecular design platform can be expressed as trifold computational integration. There is, number 1, machine learning and deep learning. This enables the ideation and exploration of vast chemical space, so billions or even trillions of molecules can be evaluated quickly to discover high quality and novel molecules. Then as a second component, we have physics-based modeling, where the molecule's key properties are predicted with an accuracy at least that's the idea, comparable to physical experiments. And the atomistic molecular modeling then would enable the precision design of molecules as a consequence. Enterprise informatics would play then the third component. Live sharing of computational and experimental data and design ideas for rapid decision making is one key component. The other one, easy access to expert computational technology and models, as well as cheminformatics for collaboration across multiple locations. Our molecular design platform has to run on a platform, and we designed it such that it is supposed to run in a cloud environment. And with cloud, I mean a cloud architecture as designed by, for example, Amazon, Microsoft, or Google, but it could also be your in-house cloud. The molecular design platform is designed as provider agnostic. That's important for us, that's important for you. What's also important to emphasize is, which is a major concern to everyone, security. So what do we do to make sure that a platform system is in a secure environment? So first and foremost, all traffic to and from the platform over the internet is encrypted in transit using HTTPS with TLS encryption, which is today's standard protocol for encrypted web traffic. Access to the platform login portal can be further locked down using cloud provider firewall rules. For example, only allow access from a single site. Scientific data placed on block storage within the system itself is automatically encrypted. When the data is then processed by the CPU or GPU, it's decrypted, of course. But if then the scientific data is transferred between instances in the system, it is automatically encrypted again. Apart from these points, we implement the usual best practices in IT to secure a system so that data cannot be accessed by non-privileged users or services. Important point for cloud computing is its scalability and elasticity. Cloud systems are scalable in different ways, which are important for large-scale molecular design workloads as the ones we are talking about here. As cloud resource providers are providing access to large data centers, it is now possible to run on thousands of CPUs or hundreds of GPUs. Although possible to have a system of a very large size on premises, it's usually a waste of resources if that system cannot be utilized 24/7. So it's possible to get a very high throughput on demand with a cloud structure. Upgrading to new hardware is just a matter of changing the configuration of the system. But for on-premises systems, as you all know, as I know from myself, hardware upgrades are usually very lengthy projects. So that's also an advantage of having a cloud provider. The underlying infrastructure, like the network and the storage, are inherently scalable as well. And first and foremost, as far as access is then concerned, there's absolutely no installation required on the client side, except having a browser installed on your computer. Let me outline one concrete example of a molecular design platform with the de novo design collaboration between Bayer and Schrödinger. In short, we're trying here to find the best 10 out of a billion new molecules as accurately and quickly as possible in a therapeutic discovery program. So what is required as a base is an experimentally solved protein target. Then, using the cloud, molecules will be optimized based on protein binding affinity, physical chemical properties, as well as synthesizability. And at this point in time, I'd like to mention that these components of the molecular design platform are coming both from Schrödinger as well as Bayer, which is made possible by having designed an open architecture for that platform. Here, in short, the technology from both companies that are getting coupled. We have Schrödinger's physics-based affinity prediction called FEP+, which stands for free energy perturbation. Bayer's knowledge-based models for absorption, distribution, metabolism, excretion, toxicity, as well as its synthesizability estimation. And in the workflow from getting 1 billion down to the top 10 molecules, physics-based modeling gets constantly combined with machine learning. The third element in order to handle all the data and analysis is Schrödinger's enterprise informatics component, Live Design. It all runs on the cloud, but a de novo design platform that is supposed to have impact on the specific drug discovery programs at Bayer that tend to change over time, as in all pharmaceutical companies, certainly can neither be deployed nor accepted overnight, so it is designed as a long-term partner alliance. Let me outline how this interplay between machine learning and physics in a molecular design cycle may look like. From a compute time perspective, it is faster to enumerate billions of molecules and filter them down with either knowledge-based algorithms or simple physics-based methods. Let's now assume that such a filter process gives you 1,000 molecules, which properties of interest will be calculated with rigorous physics-based methods. That solves two problems in the beginning of a research program. The first one, you may not have enough experimental data. So you take the accurate in silico data to then, number two, train a machine learning model, and based on these, enumerate again up to 1 billion molecules, which are then filtered down again, say, to the top 5,000. And since you will not make these 5,000 compounds in the lab due to cost and time, you run them again through an accurate physics-based model to calculate multiple properties to, say, give you the top 10 molecules. Decisions will be made and have to be made by experienced researchers, so you may come down to the conclusion that the top 10 in the first round of iteration are simply not good enough for you, and you go through another design iteration and so on until you making the decision, okay, these top 10 look great, that's the one that I will be synthesizing. Let's now go another level of detail deeper to look at a concrete molecular design example. We have recently published this proof of concept design process based on the pharmaceutical case of optimizing a CDK2 inhibitor, where we focus on optimizing the molecular property of binding affinity to the CDK2 protein target. The same principles would apply to other design problems, say solvation and viscosity of polymers. Suppose somebody gives you that CDK2 lead compound. What if we were to substitute the biphenyl? What would be the possibilities? Suppose we were to retrosynthetically decompose our lead compound in a library of molecules based on commercially available halogenated areals using our Pathfinder software. That would give us about 300,000 compounds. A property and docking process would filter those down to about 70,000 compounds. This is on the one hand a reduction from the original 300,000 compounds, on the other hand necessary to get 3D information of ligand binding. 70,000 compounds are too many molecules for accurate physics-based calculations using free energy calculations, so we would put in a deep learning step in between, which is called active learning. How does it work? From the 70,000 molecules, we would take 1,000 random molecules and run the physics-based method FEP+. The outcome would be used to train the machine learning model. Then we go through a next round of learning. Are there any changes in the affinity estimation in the machine learning model? If yes, so we would start a new round of calculations. If no, we would simply stop any further active learning calculations. We would then run full FEP+ on the best molecules. With that kind of setup, we introduce computational efficiency. Here in this case, 61% of the estimated best molecules were found at about 6% of the compute time. The active learning FEP+ scoring was pretty encouraging. As a reminder, the generated compounds were based on enumerations of commercially available building blocks. It would be now great to get more molecular diversity in place without getting into non-desired chemical property space. This led us to the exploration of deep learning methods. Deep learning methods yield a function of a molecule to return a value, and generative deep learning methods try to find the optimal value in molecular space by calculating the first derivative. We're currently testing these methods here. I'm just showing them for the sake of transparency. And now going back to our case, we are training the chemical space with the approximate 100,000 compounds from our enumeration example, which survived the docking into the protein target, and now train our deep neural network with the affinity value obtained with our physics-based method FEP+. On this slide, you see again our biphenyl compound number 1A, which is enumerated based on commercially available building blocks to the enumeration ensemble, here marked as compound number 1. So that compound number 1 provides the input for the generative learning molecular ensemble on the right-hand side of the slide. On the lower part of the slide, you see two colorful funnels to rank order the best compounds, and from each funnel, we then take the best 250 compounds. The left-hand funnel is the one I showed you before, based on the enumerated molecular ensemble using active learning FEP as a last step. And on the right-hand side, that funnel is based on the generative learning molecular ensemble, which tries to generate molecules based on multiple properties containing affinity as well as physical chemical properties. All properties of all molecules are calculated. There is no experimental information available here in this proof of concept study. The deep learning method we have used for the generative molecular ensemble is based on reinforcement learning. The reinforcement learning approach uses 3 neural networks to generate molecules that are optimized for multiple properties. No ground truth is really required. It simply uses a reward-based system that is supposed to answer the question, did this action produce a desirable result? For the de novo design, a prior network is trained to generate smile strings, which represent molecules. A scorer network then evaluates those strings with regard to the properties of interest, and an agent network is taught to generate strings that optimize scores. It is interesting and relieving to see that the prior network that was trained on the enumerated compounds from the biphenyl substitution generated in about 96% of the cases the right core and the R groups. The scorer network, again, is supposed to evaluate a smile string based on multiple molecular properties. So essentially, the scorer is doing multiple property optimization. The rate limiting step in our, as in most in silico workflows, is the most expansive calculation, which is here the physics-based affinity calculation FEP+. So let's now perform FEP+ calculations on only 500 molecules and check how many of those molecules are tight binders. On this slide, you see 2 enrichment tables for affinities differing by an order of magnitude. The trend in both cases is the same. The molecular ensemble based on generative learning shows a 6.4-fold enrichment of highly potent compounds over a random selection, and it has a 1.5-fold enrichment over the active learning ensemble from the enumerated compounds. So one can argue 1.5-fold enrichment, that's not a lot, but since the compute time is cheap, of course, you're going to take the 50% improvement. This slide here shows the molecular diversity of all generated ensembles, whereas X and Y-axis represent a diversity matrix. And what's here great to see is that the different approaches produce different chemical space and potent molecules are among all of those different spaces. But the real question in the end is, are these computer-generated and computer-calculated molecules real? Since this is a computational proof of concept, we haven't done any experimental studies, but we compared all potent inhibitors from the computational study with known CDK2 or other kinase inhibitors. And indeed, what you see here is that these colored substructures that match exactly known CDK2 inhibitors are matching the compounds that came out of our workflow, which is a fantastic outcome. This work was published by my colleague Robert Abel and his co-workers 3 months ago on Chemical Archives. So here you can have a further read if you're more interested in further details. So that Chemical Archive is from 7th of February 2020. So let me highlight now 2 recent collaboration press releases about molecular design platforms. Needless to say, it's great for a small technology company of 400 people like we are if giants like AstraZeneca or Bayer partner with us, but that alone would probably be pretty boring for you. So what I think is not boring, in my opinion, is what exactly is said in these press releases. So in case of the AstraZeneca press release, the key here, as mentioned, is to deliver higher quality compounds more effectively, which would mean better and faster at the same time. If this could be achieved on a variety of projects, that would indeed be transformative. Bayer puts the computational chemistry directly in the context of digital transformation, which is simply amazing if you compare this with the expectations of computational chemistry in the field not so long ago. That brings me to the summary of my presentation, which I titled Consequences of the Molecular Design Platform. Deep learning shows great performance in both ideation and virtual screening, but it's really not disruptive in ultimate prioritization of molecules. That really is reserved to physics-based modeling, which is the key technology to separate signal from the noise to find the valuable outliers. And the molecules of interest all have properties that are outliers. Experimental and virtual data will democratically sit side by side, so they're equally accessible and they're both base for decision making. And especially in the beginning of the project, the virtual data will become more and more important because the accuracy is getting better. And in the beginning of the project, you do not have many experimental data available. And that really represents one important key component for the digital transformation of R&D. It's kind of ironic that so-called artificial intelligence generates a lot of jobs for human beings, which has a lot to do with the need for contextual competence, which is based on a lot of human input and collective intelligence opposed to artificial intelligence. Actually, there's a big chance that more human designers than ever are required for molecular ideation and original ideas, whereas the computers are doing what they're good for, enumerating at large scale. Also, supervision of a complex digital workbench requires a huge amount of human contextual competence. So that would bring us to a pretty pleasant division of labor between computer and people. So rather than shoveling data and organizing sheets, humans could focus more on design and process supervision, and the annoying work like large-scale enumeration, organizing and evaluating billions of data points would be done by computers. So that requires a sophisticated enterprise platform which is capable of registering, organizing, and analyzing billions, trillions of virtual compounds, as well as experimental data. Thank you very much for your attention, and I'm looking forward to your questions.
Well, many thanks to Jörg for this interesting and comprehensive insights. I am sure that there will be questions from the participants regarding your explanations, which you will now address in a minute. First of all, a note to the audience. You can still ask questions by entering them below the presentation window. I see that we have already questions coming in, and I would like to start the discussion with the following question. How small startup companies can use this idea of platformization to their effect? With limited resources already, workload is shared between departments and employees. In your opinion, how can we use this approach to increase the productivity and the probability of success? So it's up to you, Jörg.
Okay, thank you. All right, so how would I answer this question? So as I said in my conclusion, I mean, the opportunity of platformization means that it's possible to have a huge infrastructure built that is then managed by people. So rather than what many small companies do, they build an infrastructure in-house, they build it up from scratch, it's possible to have essentially a cloud-based infrastructure that has this entire machinery of calculations customized to the specific research goal of an R&D organization, even if it's small, and then having this organization focus on what they really want to achieve, which is, making decisions with regard to their research goals. So I would say it's almost perfect for a small organization, especially in the beginning when you start an organization. You may have a few experimental data. Your small company may be defined on a few interesting cases, a few outliers, something exciting and new. And then based on that, you want to run any kind of molecular design. So you probably start from scratch, and therefore having a in silico machinery built out already, fully working on a large cloud system is a very good opportunity for such small entities, in my opinion.
Just a question from my side. Do you have specific licensing models for startup or, let's say, smaller companies?
I would say the fair answer is it all depends. So I would say it all depends means, whatever the problem is, we'll find a solution.
Okay. Thank you very much for that answer. The next question is, modeling has been around for some time. What is different now to make it really successful?
Yeah, there are two things. I mean, if you really think about the field of in silico computing, what really the driving force is, one of the major driving forces, has actually nothing to do with software. It's the constant optimization of the integrated circuit that has been developed in the 50s of the last century. And that results still into Moore's law, and that Moore's law is still amazingly valid. So that means every 2.5 years, the computer speed doubles. That means for the same amount of money, you get twice as much. So that's a geometric explosion of computational capacity. Then on top of this, we have now cloud-based computing that allows you to scale things up enormously whenever you need capacity. So that in combination with Moore's law gives, of course, a outview into the future, which is truly amazing. So very complicated calculations today will be standard in a couple of years due to this geometric explosion. And that's really the difference to any linear improvements. As we all know now from the Corona world, anything geometric is, of course, one thing. The other thing is that provides opportunity to optimize algorithms and optimize software, and that's why many efforts will go in this field. And we're just one example. We're a company that is now 30 years old. And in these 30 years, we, of course, have benefited from that, and that allowed us to develop new software. So in that sense, I think these would be the two answers.
All right, thanks. The next question. In your presentation, you focused on molecular design. Could you comment on the possibilities to describe mixed target products, such as composite materials?
Yeah, okay. In a sense, I already presented composites just from the life science world. I mean, if you think about a drug in the context of its environment, a protein fully solvated, that's a very complicated, system. And that can be treated with physics-based modeling in the same way as composites can be done. So you have non-bonded interactions of a large system that can be treated very well these days. So yes, of course, you can do this for all kinds of molecular design. And as I said before, the systems will be getting larger and larger. So therefore, the physics-based modeling will, by definition, play a more important role in the future, because even large systems that they cannot treat today, you will be able to treat tomorrow.
Okay. Thank you very much for that answer. So we have a lot of questions coming in. I have to just take a look which is the next one we are going to. Okay, the next question. For organizations that are already invested in a platform like Dotmatics or CDD, how can these be integrated with life design?
Yeah, that's pretty simple. Based on the information I gave before, life design has an open architecture, so you can plug anything in, and therefore it can connect with anything. It has to be like this. Essentially, any computer system has to operate like a coral reef. It has to be fully integrational, so that we have this colorful world of integration with all colorful fish of any sort and size that interact with each other. So that's the same case here. Software providers nowadays don't have any longer closed systems. This is not going to work. So having an open system is really key, not only for life design, but for all other systems as well.
Okay.
So you can take advantage, in this case, like Dotmatics, you can take advantage, let's say, of the analytics capabilities, and you can combine this with a life design layer and, make that seamlessly works. No problem.
Okay, thanks. Well, the next question. How big can the research organizations be that use such a molecular design platform? What is your experience here so far?
Okay, so there's at least one public example. Nimbus Discovery, for example, in Boston, is a company that is relatively small. And there it was reported that drug discovery is essentially done in the way that you have people who have a core expertise in making decisions, and the rest is essentially then either outsourced or or really put to in silico methods. So that combination really works. That's one example. There are many other examples. So I would say, to answer the question, should be at least one person. I don't think it's going down to zero. That's an important message for the talk. I don't think that computers on their own, just interacting with each other, will create value. There needs to be human supervision. Somebody needs to make the decision what makes sense. So that contextual competence is important.
Then the next question, is the platform for free or do you have to pay annual fees, or you pay computational costs only, or annual and computational costs, and is there a trial version only?
Yeah.
We've touched on the licensing model, but this is a more elaborate question on the topic of pricing.
Okay. Yeah. So first of all, Schrödinger is a commercial company, so we need to finance our organization from the business we're doing. So therefore, it's not for free, and it's the usual market question. If it provides value, then people will pay for it, and that's the case for any business, including our business. Concretely, we usually have annual fees for software, and then also, since we're working together with partners to integrate, it can be an integration of data, third-party software, our own components, to do whatever is necessary in order to solve a R&D problem. There would be then also potentially a service component.
And as you mentioned in your presentation, the savings regarding computational time and therefore maybe time to market are really astonishing, because I think you said you identified the targets with 6% of the normal computing time, if I remember that correctly. So it really makes a huge difference to use a system like that.
Yeah, that's right. And again, it's getting better and better every year. But I mean, every R&D organization needs to evaluate what's really the best mix of experimental equipment, in silico equipment, human decision making, and that really depends on the research problems. So in that sense, for every specific organization, even for each project, you probably have to answer that specifically.
Okay, thanks. Going on to the next question. How are machine learning and molecular design related? What is the relation between these two methods?
Yeah, I would just repeat what I said in the conclusion. In any kind of computational funnel has to be designed such that in the last step you use the most time-consuming step, which only makes sense if it's really accurate. We believe the accuracy has to come from physics-based models. They are more time-consuming than machine learning models. Therefore, the relationship is that machine learning plays a fantastic role in prioritization, i.e., scaling down from billions or even trillions of molecules to the top thousands of molecules. But these top thousands, there you want to make sure whatever you synthesize really makes sense. So then you have to use the more time-consuming methods. So then, of course, there is the question, do you have a physics-based method which is accurate enough? That needs to be answered for each system. Is the physics-based method fast enough for the given problem? That needs to be answered based on the compute power available and the complexity of the problem. And that defines then the quantity of this funnel. So if you start with a few billion compounds and in the end, you have only time for physics-based methods to do 100 calculations to then synthesize the top 10. That's then the answer. But my firm belief is that machine learning methods alone, since they're based on interpolation, will not really be suitable for doing the entire molecular design. So we're looking for outliers, weird molecules. I mean, successful molecules are in a sense completely weird, strange molecules. And finding something strange, in my opinion, is reserved to physics-based methods.
All right.
Strange in a good sense, I mean.
Of course. Thank you for that answer. The next question. Is hardware development also accompanied by platform and cloud computing? And what are the challenges?
Okay, so the recent advances in hardware, like the GPUs they were really not invoked by any kind of platform, at least not a molecular design platform. They were invoked by gamers. The gaming industry produced these very fantastic cheap GPUs, and they, since they're massively parallel, are now fantastic for some computer algorithms, and that brought down the compute time. So in that sense, I would say I don't necessarily see this at the moment, but on the other hand, there were some algorithms. If you look, for example, at the compute time on these cloud systems like from Google or Amazon, a couple of years back, most of this computer time went to blockchains that had a lot to do with the Bitcoin industry that went down a little bit recently. But technologies like this with Bitcoins, blockchain technology that is still being used, also in the context of what we're doing here, potentially. At least there's some experiments going on. So I would say, in molecular design, one should always be opportunistic what's going on in other industries, that driving a certain hardware improvement, and then see what is suitable. I think that's the great thing, that whichever industry drives a certain development of hardware helps also the other industries. In that sense, it's pretty collective in a positive sense.
Okay, thanks. Going to the next question. Can we find out toxicity of the molecule through molecular design? Is that possible?
That's a very good question. For that, we need to have, if we want to do it physics-based, we need to be able at a certain point in time to treat much larger systems, like an entire organism, with physics-based methods. So I would see in the next couple of months we will not be able to do that, but in decades maybe. So therefore, again, if you can't treat these important questions with rigorous methods, you would then have to use any kind of knowledge-based systems, and that's what's going on. These knowledge-based systems are not just noise, they're actually better than random studies. This is what these knowledge-based systems show, otherwise they wouldn't exist. As I also have shown in the example in the collaboration with Bayer, the Bayer toxicity models are going to be used in that kind of context of the platform. And Bayer, with a huge experience and a huge wealth of data and programs, certainly has optimized them, is pretty proud about them, and should be proud about them. So yes, toxicity and molecular design are related.
Thanks. Oh, the next question, quite current topic. Molecular design simulation has been used extensively to find COVID-19 treatment. Can it be considered as a standard in drug design nowadays? What's your opinion on that?
Yeah, based on what I know about the pharmaceutical industry globally, molecular design, in silico molecular design, I mean, we're doing molecular design now for thousands of years, but in silico molecular design, is certainly something that is standard these days and will become more and more standard, and will become more and more the, let's say, the driving force for molecular design. COVID-19, yeah, there are a few alliances, some of them public. We were involved in one alliance, in one global alliance that has been published a couple of weeks ago in Chemical and Engineering News. And yeah, molecular dynamics are also nowadays a standard for such molecular design discovery. So the answer is a clear yes.
Okay, thanks. Next question. How affordable is the use? Life science is great, but material chemistry or composites provides less profits. So yeah, we were talking on the investment costs compared to the rewards when using this system. So maybe you can just quickly touch on that. Yeah,
okay. So as far as profits are concerned, I mean, there are very different numbers around. I mean, some people say the entire life science industry is not profitable if you take into account the entire investment. But of course, some companies are pretty profitable. All right. But anyway, so this is not a discussion about profits. It's about, is it feasible? So I would say, like with anything that has to do with computers and Moore's law, since the compute time is getting cheaper and cheaper every year, by definition, therefore, in silico methods are getting cheaper and cheaper every year. It's not necessarily true with experiments, so therefore I think in comparison between experiment and in silico will probably win over time. But of course there are also experimental setups that are getting more favorable, but I don't think in such a sense as compute time. Then of course there's the question of what happens then with the software, but if you just think about it depends on the licensing model. But usually, if you can compute things faster, so the average software price goes also down. So I think this entire trend is in the favor of all molecular design for all molecular design industries. So that's not only materials, also the food industry, widened green biotechs designing bacteria to produce fuel. All of this will be essentially driven more and more by in silico molecular design methods.
All right, thanks. So the next question, how can this method be used to improve enzyme design?
Okay, so that's what I just mentioned in my former example. So it's the same here. I mean, an enzyme has a certain function, and that function can be calculated in the context of that probe or that molecule that is supposed to be, changed by the enzyme, or the enzyme is supposed to be, blocked by. The molecule is supposed to block the enzyme. So let's say molecular interactions between an enzyme and a ligand can be clearly calculated. So you can do this in the reverse way. So you can design different enzymes. You simply exchange the side chains of the enzyme, representing a different DNA representation for that enzyme. So you mutate the enzyme through and calculate the interactions, and then see whether the function of the enzyme is more optimal with regard to what you like to achieve. So this is also standard these days, and you can also do this with free energy perturbation. If you're thinking about optimizing an enzyme, that's the way of doing that. So rather than changing the ligand, you can change the enzyme, because you're also calculating the interaction energy between the two.
All right, thanks. So I think this will be the last question. Maybe, if possible, a quick answer to the following question. Could you please comment on whether the FEP-based physics methods could be further improved by including quantum chemical components?
Yeah, so first of all, it is already improved, because the free energy method uses a force field. It uses molecular mechanics, so therefore the interactions of atoms need to be parameterized. They're parameterized and optimized with quantum mechanics methods. That's one possibility. So the other possibility is to come up with an interface between quantum mechanics and molecular mechanics. Such interfaces exist. We have them as well. So for some key interactions, you can define, let's say, a region as a quantum mechanics region, and the rest is then treated with molecular mechanics. That's a computational efficiency that you have here. And then what's also reported in the literature, you can combine quantum mechanics with machine learning models in order to have a faster quantum mechanics approach, so that it can use it more in high throughput. So there are numerous ways of including quantum mechanics in various workflows in order to make use of them. And then again, for the given problem, for the given compute time, one would then choose the best combination.
Okay, great. Thank you very much, Jörg. Unfortunately, we have reached the end of the webinar, and so I will close the Q&A session now. As already mentioned at the beginning, our expert will answer all outstanding questions by email afterwards. I would like to thank all participants for their interest. Special thanks again to Jörg Weiser for his excellent presentation. And I would like to conclude by pointing out once again that we have recorded today's webinar and will soon be making it available on our website caremanager-online.de/en. You will be informed by us as soon as the recording is available online. Once again, many thanks for participating in this webinar. Have a nice day, stay healthy, and see you at the next Care Manager webinar.